Yeah, hi. Obviously, as I said, that's the nature of my talk, where I'm going to be talking about basically how we're going through all of the different processes of rendering, really. So who I am, thankfully, I got an extremely flattering introduction just then. But essentially, I've spent probably about probably 10 years making games and doing sort of game development stuff for the last little while. I actually work for Tin Man Games at the moment, doing Warhammer Underworlds Online. Prior to that, Table of Tales. I ran my own company doing Rogue Singularity. Did a game before that called Warlock of Fire Top Mountain. So I've got a bunch of different sort of release titles kicking around. And so I'll run through just some of the basic terminology that I'm going to be going through in this, which is talking about things like files, shaders, textures, models, materials. These actually don't necessarily have technical definitions, but are frequently used differently and whatnot. But just as a general breakdown, the file is actually your data as stored on on your Windows system or what have you. That's the thing that you save from your you save out of your software package. Shader is specifically the code that is going to display things on screen. Your texture is what gets applied. Well, I've really put this in a very foolish order. The model is what your software package is going to deal with. So usually it will convert your file into the model data. Model data can often be different depending on the game engine. Then your material is what is basically applying any settings and textures that you have, and that material information is presented to the screen through the shader. So the shader is basically reading all the information it needs from the material in order to display a model. So I'll go through this in some more details very quickly. So basically, as I'm sure everybody's aware, there are so many different pieces of 3D software that are specifically designed to create 3D models. But in many ways, it doesn't matter what underlying software you're using to create your modeling programs, it will eventually get crunched down into data that has to be run by your game engine. The important thing, to an extent, to understand about your the way your modeling program is dealing with your underlying 3D models is that obviously a format is just an ambiguous concept that deals with the information that's regarding the surface of your geometric object. And the more information that you can store about that geometric surface, the more powerful your model and the more things that you can do. That underlying storage mechanism isn't universal, and there are a whole lot of different ways to model that will fundamentally change the way that data exists inside your software package. And as you transfer from one program to another, you will either lose or gain different pieces of information about your surface model, and when it finally comes into your engine, you will also then lose specific pieces of information. So the example that I gave down here is just even in one centered piece of software, this is an example of an edit mesh versus an edit poly in 3ds Max. And what's happening in this particular one is that there are two different model formats, one of which keeps your vertex order consistent, and you're just moving around the actual edges. And you can see there that you immediately get error surfaces as they don't match up to how you would expect your model to do it. Whereas the edit poly will restructure the vertex order on the surface face of the model in order to allow for an unusual shape. And it does that by basically storing its understanding of the surface shape in a different internal format to what you might expect. So if you've ever been modeling and suddenly you discover that a operation that required vertexes to be in the same order suddenly doesn't work, so a morph target is a fantastic example, or sometimes when you skin a rig and you need to change something, but changing the vertex order causes it to break. Well, this is sometimes what's happening. What you're doing is you're losing the underlying data of what your actual vertex number was. This is also where you can experience non-manifold geometry, and that is where, due to some sort of error process, a piece of geometry gets structured that can't exist. So this might be a triangle where two sides are the same. which creates sort of like a weird squished line. So really, when we're talking about how we render stuff to screen, we're talking typically about two specific methods. There are other methods, but I'm going to be focusing mostly on the process of rasterization. Rasterization basically is the effect where we flatten our triangles we flatten our model onto the screen and then render out the pixels for the areas that each of those triangles cover. Whereas when you do an operation like ray tracing, what you're doing is you're mathematically deriving a ray going through your screen or from your light source to your screen in order to determine what the image should look like on the screen. And ray tracing is becoming way, way more common now, especially now that they've started to add some of the basic components for generic ray tracing onto GPUs. Really, the way that the new GPU systems are handling it is they take all of the triangles of your base model and they turn them into a generic format for being able to do ray tracing against, so that you don't have to basically run each individual triangle. You can do a generic request to say, does a ray of this, on this position at this angle at this length hit a surface? Tell me about that surface, and then I can construct a ray from that. Whereas it's very undynamic the way a triangular rasterization works, is where we're flattening it onto the screen. So you're losing a lot of information when that flattening process happens. So obviously, as you heard me talking about, rendering fundamentally uses triangles. There are supports for quad renderers and spline renderers, but the main reason why we use triangular rendering as the basis for everything is it's the simplest, least ambiguous surface. And so I gave a really quick example here where I've created a quad, and the shape of the quad and the way that it bends fundamentally changes based on the way that the surface is triangulated. If you're doing this operation, if you're exporting your models in quads, this is where you can begin to see very unusual bends and kinks in your model where you didn't expect it to see it. And essentially that is because you are allowing your game engine to construct the missing triangles that it doesn't have through its own internal triangle reconstruction process. And this can cause two problems, one of which is it can cause bending in unusual directions. And the second thing that it can cause is it can create circumstances where your textures will get stretched in an unusual manner, because when you were doing it, your art editing program put your triangles in a different sort of order. So really, when we're talking about formats for exporting our models, I've actually written an OBJ importer before, and so it was interesting to look into the internal of it. I won't go into a whole lot of detail, but basically what happens is it takes whatever you've created in your software package and bakes it down to just a series of vertex points, and then an order of triangles or an order of quads where it says, hey, here's all our vertexes, here's all the information for our vertexes, and then it creates another list saying, here's a triangle, and from my previous list of vertexes, here's the vertexes that make up this triangle. And then basically on top of that, we end up with more and more sort of information getting appended to that, like what is the material, what are our smoothing groups. And OBJ is a very simple format, not very complicated, and doesn't store a lot of other bits and pieces like animations, and there's certain other limitations in terms of things like morph targets and what have you. Yeah, like, so the pretty much unified standard that most people are exporting in is the FBX format, which is created by Autodesk. I've sort of at times described it like daylight savings. There was a logic to it at the time, but now we're sort of stuck with it. It is a big sort of quite complex shape that is got a lot in it, a lot of information in it, which is really really beneficial and really really effective. But it is very complicated to deal with. I do not suggest going too deeply into it, because it is not what I would describe as a spectacularly simple format to deal with. And I've certainly seen people find yourself, if you're writing your own engine, find yourself a third-party tool in order to be able to deal with it, because it's quite complex, but fairly well documented, all things considered. Okay, so the other important thing to understand about this is once your FBX model is brought into your game engine, the importation process will transform that very specifically. So what happens is it will break it up into parts that are specific to the engine and how the engine decides to construct it together. So really more importantly here, you have to sort of understand that your FBX model is going to be deconstructed and reconstructed in your importation into the game engine. And so what this means is that your actual FBX is not the thing being displayed on screen. There's a middle step which is occasionally obfuscated from you. And in Unity, you have importation commands where you can actually restructure the thing that's being imported before it becomes the model that you use specifically inside the game engine. So that can be a really important factor to understand because, and Unreal does exactly the same thing as well. This is important to understand because it's easy to forget that the thing that you're rendering on screen isn't necessarily exactly the FBX file that you have sitting outside of it, which is often why people will go backwards and forwards and what have you like that. So when your model comes in, really what happens is you've essentially got your base data here, which is X, Y, and your positions in X, Y, and Z coordinates. It's got normal information. It's got texture, UV information, all of this sort of data. And it's all sort of constructed around this idea of, what a certain degree of relativity. And in this particular one, what it means is, okay, if my vertex is at position 202, say, where is 202 in reference to? That's a meaningless statement because you need to be 2 meters off, 2 meters off, 0 meters off compared to something, and that's really what we talk about when we talk about world space and model space. And so when your model from the engine then becomes translated into your actual space in your game engine, that creates translation where you have a local space and a world space. So your local space becomes, where are my vertexes compared to where were they constructed in my model programs? And then the second question becomes, where is that vertex constructed in the world, essentially? And you have to remember that the model space tends to be quite a nebulous concept, especially when things come down to the way engines batch and do things for performance. So what happens is we might take 3 objects and combine them into one, and thus our world's object space becomes universal to those 3 specific models that have now been merged into one. So immediately your model space can merge and shift as things go along. Whereas your world space, it won't be shifting. But there is one more space, which I haven't included in here, but that's essentially your camera space, which is where is things compared to the camera. Because when rendering the object, that's what cares about it most. But when you're modeling and it's getting rendered to screen, really the main concern is world space. So quickly, I'm actually going to talk about something which I have often joked about, which is the hill that I am willing to die on, which is which way is up? Is it Z or is it Y? So really what we're talking about when we talk about this question is we're talking about the Cartesian coordinate system. So in this particular construct, I've used the terminology that was used just to get us outside of actually using the words X, Y, and Z, which was usually called the abscissa and the ordinate, which is to say your 2 primary orientations at 90 degrees to each other, with your abscissa usually being your horizontal and your ordinate being your vertical alignment. The thing that's important to understand is that structure is supposed to be oriented towards your surface plane. The applicate, which is not quite the right term, but what that is it's the 3rd right angle to those planes, which is the projection in or out of your surface. So the real reason why this argument keeps going around and around is because it depends on what surface you consider your graph to be on, your projection to be on. And only once we started aligning our screens vertically do we get this idea of X being our pixels along there and Y being our pixels up here and then Z being our pixels into the screen. However, it is categorically incorrect to say that Autodesk or Unreal using Z up as being incorrect, because both of these programs were constructed based on how everybody else has always, throughout the entirety of human history, understood the way in which our basic drawing projections work, which is in or out of our specific surface planes. And really, the main thing here is that what we understand to be our surface plane, which is technically the camera in a video game, which is X and Y. However, this is actually an incorrect assertion, because technically then all of your objects are moving and your camera is remaining fixed in your environmental projection, which means that arguing that Y as being your up orientation doesn't make sense, because you don't have a constantly shifting position for your objects in world space. In fact, what you need to do in order to establish what your projection plane should be is look towards what is a constant in your game structured in this environment. So in this one, most of our understandings becomes the what I argue, which is the gravitational constant, which is a vector. But vectors can also, in this structure, represent a surface. So in this particular construct, we have, if you are given a position, which would be your abscissor and your ordinate of an object within your world projection, when you construct your world orientations by arguing for an XY orientation, what you get is the image on the right, which is sort of nonsense. Whereas if you have your Z plane as your projection up or against gravity in your cardinal coordinate system, you end up with a much more sort of sensible one in your actual 3D environment. So I would say that the original 3D programs that processed a Z being up were technically the ones who were originally correct. And it was only when we went into 2D games and had X and Y pixels that we started to develop this idea of why, well, really probably started off, I would imagine, with both graphs and really being done in a, on old tube TVs where you'd have like the lines going up and down, would really have been where you started with your Y being up and your Z being in and out of the screen. So my argument is that Z is up, and I will die on this hill. So jumping into other pieces of stuff. So once we get through this, basically what we do is that vertex basically all of your model essentially gets constructed down into a series of pieces of vertex information, which is just a single point. So a vertex is just a structure of information. So it will have your position, it'll have your normal, it'll have your tangent, it'll have your vertex colors, and it will have sometimes up to 4 or 5 UV coordinates. Now, a UV coordinate is just a data channel like position or normal. And in fact, it's very little known, because I guess we just don't use it all that frequently, unless you write shaders very commonly. But UVs support a W and an A. So in fact, most UV coordinates actually can have 4 values stored within there. And frequently when you're doing shader work, you'll use texture coordinate as a universal for passing information from your vertex to your fragment. So really in this one, your engine is sending through more data from that model than you might realize, and there's more data that you can attach to that model than you might realize. That information from your model, so your vertexes contain your normal information. And what your normal information is the direction that vertex is facing in, really. And that's where another sort of not particularly well understood concept comes from, which is what is a tangent and what is a binormal? Well, actually easier to understand than you might think, which is essentially your tangent and your binormal are your right angles to your normal. So that is, my normal's up, my tangent's in one direction, my binormal's in the other. And this is what they talk about handedness, which is which hand are you using in order to calculate all of this stuff. But in this structure, really, you have to look towards your engine for how all of this stuff is. And import settings often have different ways of calculating your tangents and your binormal, although it frequently is constructed sort of from your UV space to an extent to understand what your surface is doing. While a normal is a vector, without necessarily having length. So that is, it's just a directional vector, which means that its magnitude is 1. But that doesn't necessarily always have to be true. So that means that your normal values could actually be larger or smaller than 1. They could actually carry more information through with them than necessarily just that. This will make a little bit more sense when I get into the lighting section, but this is just a little bit of primer for... It also helps you understand why... this also helps you understand why your normals, essentially, in this context, are... why you use triangles, because then it means that your normal is the surface-facing direction for your triangle. Otherwise, you would have a little bit, you could have strange bending associated with it if you just have one triangle. So basically, we've got this information on screen now, a bunch of vertexes all distributed around the screen with their information in them. How do they actually become rendered to screen? Well, it's relatively straightforward. Basically, your camera has a frustum, which is your view projection angles, and usually most of your engines will decide what can I see, what can't I see, and then it discards objects that it can't see. It does any occlusion culling that has got built in on the computer side of the engine. So you might have, say, hey, if this volume is in front of me, don't show any of the stuff done in that. Then what it does is it constructs a series of buffers, which are essentially your calls that are going to get made to your GPU. And it could do your dynamic batching during this process. It could do your static batching. Basically, static batching is before you run the game, it takes all of your objects together and it combines anything that has the same material and the same model into one single object and then sends that through. Same thing happens with dynamic batching, but that happens as you're moving your camera around. So what it'll do is it'll only clump together objects that are within your view frustum, and it'll happen as the player moves the camera. And basically what that does is, if you were just rendering a cube, it says, take these 5 cubes, turn them into one model with one new object space, and then send that to the GPU. And these commands that we're sending to the GPU is a little bit of a bottleneck and can't send through all that much information. And so what it does is it tries to optimize that to send through the smallest amount of information through towards it. And then basically it waits for the GPU to synchronize with your CPU in order to make sure that both of them are running it at the same frame rate and sends that information through. So when you are CPU bound, that's why you will be able to see that stuttering. When you're GPU bound, that's why you will also see that stuttering, because both of them need to be working in tandem in order to be drawing everything to screen. Once we've sent it to the GPU, you usually will do the depth buffer path. You can do a pre-depth buffer pass, but what we'll do is you render the objects. As each object renders, it renders itself into the depth buffer and draws all the objects. And once it's done that, then you run whatever screen effects need to be done, like reprojection or any post-event rendering and what have you like that. So that's basically the process by which the system is doing the rendering through your engine. So really the way that the screen rendering works is that it is averaging the values of the 3 vertexes that create that triangle. So what will happen is it will be sent through a list of triangles. Those lists of triangles are going to be transformed using a matrix. I'm not going to go too complexly into this, but if we go to the previous slide, you can sort of understand that what it does is a matrix is essentially a mathematical operation, which is a singular multiplication that will take your triangles and squish them flat onto what's known as your projection plane, essentially. That is your screen play. So once you flatten your surface to the screen, you can then start rendering out your triangles for each one of those. So what we're talking about here is each of those triangles is an averaged value of the 3 pieces of vertex information that are present in your vertexes. So your model has the triangle information, but your shaders are typically dealing mostly with vertexes, and then your fragments are getting your vertexes in series of 3. So it will basically say, if I am here and my blue, red, and green are the colors of my vertexes, then my vertex color fragment in between is the value that you want. I'll also take this opportunity to talk quickly. I'm sure people have heard of geometry passes. This is where you can get extra vertex information, so that can subdivide your surface. It's one of the quite cool things. They've got it in Unreal, and if you're in the latter versions of Unity, you can do these things which are like height maps that have actual geometry associated with them. So what a geometry pass is it does not actually occur, surprisingly, does not occur before your vertexes occur. It actually occurs after your vertexes. So it intercepts your triangles as they're coming in to be rendered to the screen. And it says, here's my triangle, which consists of these 3 vertexes, after the vertex transformations have essentially occurred. And then it will say, and then you get the opportunity to append a new triangle into that list. And so what it does is you can say, hey, I know my triangle is this shape. So what I want to do is subdivide this triangle into a further 3 triangles, say. So I want a hypothetical vertex in the middle. So I'm not going to send this triangle onwards. I'm going to add a new vertex in the middle and split my triangle into 3 triangles. And then I'm going to send through triangle 1, triangle 2, triangle 3. And I'm going to give them the vertex information that I want to. And that will allow you to do a lot of really effective stuff in that way. So let's jump on to, I'll show a very tiny piece of shader code. You don't need to know it. This is just understanding how we're getting to screen, basically. So after, essentially what we're looking at here in a basic shader is your input data. So in this case, this is the data that I'm asking from the model. And that data is, what is the vertex position? And I want your texture coordinate 0. So for each vertex, we're just asking 4 numbers, x, y, z, w for the vertex. And I'm asking my texture coordinate, which is, again, u, v, w, a. It doesn't matter what letters you use. You can use u, v, w, a, x, y, z, w. There are a whole bunch of different systems for this, and often they sort of shift depending on purpose. So basically what happens here, your vertex input is your information from your model coming to your vertex. So what we're doing is we're saying, hey, we've got our vertex input, and that's where we want to do. So when I said that there's a matrix calculation that gets performed on that vertex, that's what Unity matrix _ MVP is. So we say, give me this incoming vertex, and then what I want to do is multiply it by my matrix, which is essentially take this vertex and reposition it to where it occurs on my flat screen. And then after I've done that, I also want to just pass through, oops, okay, let's go back. Also, I want to pass through my vertex to my, I want to pass through that to my fragment information, which is essentially what will then be written to screen, essentially. And there's a lot of different bits and pieces that may happen in this particular construct that can occur in this particular pipeline. This is a very simplistic element, I'm sorry, this is a simplistic overview. I could go into more detail. It's a little bit more complicated than that, but this is a good way to sort of think about it. So once it gets into the fragment, basically what I'm saying here is I want to just write out to my target. In this case, it could be the screen. In this case, it could be a render texture. I just want to render out my UV coordinate, basically, which was coming through in this. So in that case, my UV coordinate could be, in this case, I'm just writing out X and Y. So if that was here, this would be rendering out a solid color of red and green, and alpha would be 1, and my blue channel would be 0. So in this context, I would just be rendering out to my triangle my raw UV coordinates. So one of the things that gets done in this process is it's generating and constructing the depth map as it's doing this. So one of the elements part of the fragments that are being written is depth map information. There's actually other information that's also getting written, which is essentially your there's some special culling settings in there that are used, which is sometimes called, I'm trying to remember, I can't remember the name of them off the top of my head. If I recall, I'll come back to it. But depth is a relatively simple thing to understand. But basically, because my triangles can overlap each other, we have to be able to structurally understand which one is coming through, which one is rendering first, which one is rendering second, like who's in front of whom. And so how we do this is, because we know the world position of that vertex, and thus we know the world position on our plane, when those vertexes are getting rendered onto our screen, we're also rendering into a depth map, which is basically just storing how far from the camera was that fragment written. And then when we come to render our next pixels on the screen, we can look at that depth map and ask whether or not this pixel is greater than or less than the current value that exists in this buffer, and discard it before we perform the operations on it. So that's why, that's how we handle overlapping vertexes and overlapping components of the models, essentially. However, this sort of rendering is not limited to just, okay, it will just do it automatically. It's actually fairly customizable. A depth test does not have to be less than. You can also do equals to and greater than. One of the factors in here that we used actually relatively effectively in Rogue Singularity, it's not a great shot of it, but when our characters ran behind objects, what would happen is you could see an outline of the object so that you would continue to understand where your character was despite having gone out of the camera's view. And this was done through carefully controlling the order and the priority of what was being rendered. And that ended up being a very successful process for us in being able to do this. A thing to also remember is that this is basically what's occurring when you're rendering shadows. So think of your shadow casting lights are essentially cameras rendering out depth maps in order to determine that. So for instance, if you have like a pixel light that has real-time shadows on it, that means 6 different cameras rendering all at once in order to do each of the sides of your hypothetical sphere. There is a few other elements in there which basically allow for different types of culling, and they're certainly worth playing around with. But most of us are working in deferred, for really high level rendering, often working in deferred systems in which they already tend to be used. So something important to remember is that your depth precision isn't linear. So that is, your precision isn't linearly spaced all along your depth information. It's actually, for a whole bunch of complicated mathematical reasons, reciprocal of your world space depth. And this is in order to try and space out your depth precision more evenly across the boundary of your near and far plane. But it does mean that when trying to determine whether or not one object is in front of another, your precision will become an issue. So this is what happens when you see Z fighting, where sometimes an object pops in front of another one, pops behind it. That occurs primarily because you've lost depth precision. So what's happening there is you're far enough away from the camera, or the two objects are close enough that sometimes your float accuracy, you're falling on one side, and so it thinks that it's eventually it becomes striated bands. There's only so much information that you can, it's not infinitely subdividable. So eventually you'll end up with either I think we are at the same value, or I think I'm a little bit less, or I think I'm a little bit more. And when I do that depth test, you'll start slamming on either side of it. So one frame it might appear in front, one frame it might appear behind. And so the important thing to remember, why it's important to remember that your depth precision isn't linear, is because that means that if your object is a certain distance in front of another object, that doesn't mean that it won't Z fight at all distances from your camera. That Z fighting will change, and that will cause it to Z fight at different distances based on where you've placed your model in comparison to your camera. So now that your triangles are actually getting written to screen, how does it know, how does the rasterization process know where to actually frame the pixels? So this is where actually anti-aliasing becomes a big factor. So we've got our model data, we're flattening our triangles onto so we know where they appear on the pixels on the screen, and these are essentially what your Fragments are called. Usually we use the term texel, and texel is a pixel as presented on the model, and your fragment is the pixel as presented on the screen. So the density of your model versus of your textures on the model versus your density on the screen. So in this particular one, basically what happens is the rasterization algorithms on your system can detect what pixels your line for each of your edges are going to run through for your triangle. And from that, it determines whether or not the pixel is filled or not by what percentage of your triangle is filling your surface. And it does that by detecting what side of essentially the center point of your pixel your line is falling on. So you can see in here, if you were drawing your triangle onto screen, you can see which pixels would be filled, and thus you get this shape. Now, this is where it becomes really important, because as your camera moves around, your triangles are going to be moving and shifting on screen, and that's where you see aliasing happening, where pixels start to pop. Because as it slides across that zero line, the pixel will suddenly become solid or flick back, flick forward, flick back, and you'll see it flickering. And that's what aliasing is. So MSAA is a form of anti-aliasing, and I'm sure you've all seen it in your program. And what that does is it says, okay, for whatever pixels that my edge is running through, I'm going to do more samples so that I can get a proportional amount that this pixel is covered by. And this essentially has the effect of super sampling. So basically, it's as though we were rendering it at 4 times the size when we sample one pixel. It doesn't do it for every pixels, only does it for pixels to which an edge runs through. So this becomes an important aspect when you start to think about your vertexes in your model. There isn't a lot of performance implications of sending vertexes to your GPU. That tends to be fairly generic. However, there is a performance implication of how many edges are running across your pixels, because what that means is you're essentially increasing how many samples you're doing if you've got your MSAA set up, in order to determine your coverage for each individual pixel. And so that's basically what's happening. So when you have lots of vertexes overlapping each other in your scene, basically everywhere where one of your edges is running, you're creating an opportunity where you have to calculate a certain degree of anti-aliasing in order to stop getting your edges where it goes tick, 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 you know, where you get your jaggies. We also have processes that do this after we've already written it to screen. So one of the common ones is subpixel morphological anti-aliasing, often called SMAR. And I think I've actually done the wrong acronym there. But basically SMAR is where it works a little bit like a JPEG image compression works. It looks for shapes and sort of replaces them with a shape that's roughly similar. And by doing so is able to give you smoother edge conditioning by analyzing the image after it's already rendered. But that's really why aliasing is, and especially if anybody's working on virtual reality, this is why you always rely on MSAA rather than post-effect anti-aliasing. It's because post-effect anti-aliasing is usually not quite as good, and it is much more performantly expensive than MSAA. And so that's where triangles can become a real problem if you're doing a VR-based application. But this is how it's basically deciding what to write to your screen based on the information that it's given, based on the vertex information that it's given. And sometimes this information gets stored out, well, most of the time, it gets stored in a separate sort of text format that I won't go into. But basically, it stores this anti-aliasing information that tells you, for instance, what are the percentage breakdowns for this pixel's how many triangles are running over it, and what percentage to this pixel of, say, each triangle and what have you. So where this all begins to come together when you start modeling from your modeling software to your informational software is that you can begin to use this information to come together. So this one is talking about how, oh, in fact, actually, I think the slide has gotten out of order, but it's a really good example. So this was an effect that I created that didn't end up going into my old game because it was just a little bit too intensive to create the internals for the model. But this was realizing that you can have different UV sets both implemented into the one model, and those pieces of information can be read in the fragment. So even though this was one model, what we were doing is we had a UV set for the interior, going from floor to from the feet to the head, and then we had a second UV set for the body going from the feet to the head, and then we would just say for the fragment, tell me how high up you are on my second UV map, and from that height I can decide whether or not I'm going to discard it or I'm going to keep it. And one of the things is that almost all 3D programs will let you keep multiple pieces of fragment data or vertex data for your fragments in your 3D modeling program. So you can have multiple UV coordinates that you can export with your model. So another thing to think about is what's known as MIP mapping. So this is the process by which we create cheaper texture costs when things get rendered to screen. And what this does is it takes your original texture and it downsamples it into several different smaller values, and it will render to screen the smaller one if you're far away. And it does this in order to cheapen up your rendering costs, because if you're rendering a 2K image everywhere for everything always, you're going to completely blow through your texture memory, and the game will run slow as hell. So what you end up doing here is what you want to do is you want to have your understand how your texture is going to get modified when it is going to get written to screen. And what it does is it automatically creates a series of downsampled versions of your image that gets smaller and smaller and smaller. So this is where you begin to see bleeding of edges. So if in this case I was just showing I had a UV map of a skeleton here, and what basically is happening here, as it gets smaller, your edges will begin to bleed. So this is why you need bleeded edges on your texture maps often to stop this occurring. So you can see here, I've sort of zoomed in very poorly on it. If you downsample your texture and you have white right up to the pixel edge, your white will begin to blend inside your model process. And that's why you do these dilated edges and whatnot. In fact, there is a trick that you can do, which is unfortunately being made really difficult, but you can author your own MIP maps, which means you can decide what your MIP maps look like at each shrunken level and hand author them in order to make sure that they can retain the detail that you want. The tools that you want to look at to do this are the NVIDIA texture tools that have got plugins and whatnot for NVIDIA, and you're looking for the .dds texture format, which I'm not sure everything supports anymore, but that is a NVIDIA texture format that allows you to independently determine what your components are. And so that's what we do when we do our when MIP mapping is worked. And there are some really cool tricks that you can do in order to really improve your game if you get access to this. If you want to do this, you'll either need to be a technical artist or find one, but Unity does have the tools, and I believe Unreal does too, that will allow you to author your MIP maps. So examples of why you might want to do this is if you have a tiling texture, and as you get further and further away from it, you can see the details on it become really clear and the tiling becomes really obvious. You can author in your own MIP maps that will begin to remove the tiling artifacts and make them look much more smooth as you go away. Other elements could also be to retain things like text or to retain other details. Shadow of the Colossus used this very effectively when they did their why things look so good in Shadow of the Colossus at a distance, because they hand authored their smaller texture maps for when things are at a great distance rather than just letting it blur downwards. And so you could retain details and smooth others and really stylize it. Oh, this was the slide I was looking before. So this is how the effect was created. I used a UV2 channel, and there we just stuck, because UV coordinates are just data, we can stick extra UV coordinates into your model in order to determine other things. So in this one, what we did is we just wanted to know the character's height, and through that, we could do that cool rendering effect. It's really, again, important to think about it in terms of this stuff is just data and can be used in your shaders. And a lot of artists and whatnot who'll be doing this stuff through the new graph editors, they have all access to a lot of this underlying data. So one day I'll probably upgrade my talk to talk about stuff specifically to do with these material editors, but you should be able to figure it out just by asking, how do I get my vertex color and whatnot from these particular structures. So in this context, you can see here what I did is I created a plant that, like I use it often for trees, or I've used it previously to do underwater plants. And so in this particular one, what I did was I used my UV coordinates, my vertex colors, because vertex painting is relatively easy. I use this effectively to be able to determine, hey, where are my leaves at, and what are my leaves, and where do they attach to the branch, and what are my other bits, and how do they attach essentially. I promised that I would throw this in for my animator. So another really important thing to remember when you look at this is that the information coming in from your animation, all animators pretty much work at 30 FPS. And there is a real underlying problem with this because our engines don't run at 30 FPS and they will interpolate this information. So you need to be really aware when you're working with your animations in Engine that you may have to put in extra frames after you've imported it in order to solve interpolation problems. I'll give you an example of this, which is that the model data is stipulating a animation which is very poppy and very carefully constructed around 30 FPS. But the engine is interpolating frames that aren't there, and the interpolation will always take the shortest route. And what you will get is a constant base level inaccuracy across every rotation on the model, which will make otherwise really good animations, especially good animations that are very crisp done in 30 FPS, look terrible. And no engine has a good solution to this problem because every single engine will play animations back on a timeline as opposed to actually playing the frames as they were animated, one at a time. So when you hear animators talking about why can't I play this at 30 FPS, they're meaning something very specific and they have a very valid request in it, despite no one supporting it. And I have been severely tempted at some time to leap into occasional chats where programmers are like, well, I don't understand what the problem is. It just gets interpolated up to 60 FPS. That is genuinely a problem, it getting interpolated to 60 FPS. So it creates a jitteriness and it creates inaccuracies. And so the way that often we have to deal with it is by either adding in mid frames, because animators don't work at 60 FPS. It's considered very unusual. Some do, but it's it tends to be quite expensive. All right, so I'm going to this is what I was talking about before, which was that basically all of this information from your model as it gets drawn to the screen can be run really effectively through the Unreal and Unity material editors. Specifically, they are really basically designed to effectively integrate with Unity's lighting environment. And so, or Unreal's lighting environment. So what it does is it's basically a tool to translate your model and material information into the engine. And so almost all of these tools and material editors should be able to get access to this model data as you're basically exporting them and before you're rendering them to screen. So the last thing I'm going to talk about very quickly for the last 5 minutes will just be a quick spiel on lighting, because there's a cool trick in here to talk about how model data tends to be quite mutable. So the reason why we have normals on a model is essentially so that it's very easy to tell what direction the surface is facing at so that we can work out how to light it. So basically, at its simplest level, doing lighting is a dot product of your light direction against your surface direction. If they're oriented, it basically range values from -1 to 1, depending on if they're this is what a dot product does, if our two vectors are pointing in the same direction or our two vectors are pointing in opposite directions. And so that's where you see smooth and hard edges. You can sort of see it in the bottom left, which is if we share a vertex orientation, you will see a lighting boundary that will smoothly bend because, again, you're getting those averaged texels and pixels between your normals. It will smoothly bend around. That gives you a smooth surface. You can sort of see that on the square, and you can see where it splits. So that's what a hard and soft edge is. But really cool thing to note is that your normal orientation is not something that is generated by your engine. Your normal orientation was generated by your 3D program based on how you modeled your object, which means that you can hand author which direction you want your surface to face in despite your surface not facing in that direction. So you can see here this example of a plane that I have adjusted the orientation on. So in this one, the plane is slightly darker and the upward facing plane is lighter. But if I point all our normals in the same direction of that plane, then what we get is a really effective way to do like grass on the ground and whatnot. That's how you stop it from being able to see those weird things. And this has been used really effectively by a few people to create trees. So if you look at, if any of you have seen the trees in Witness, the way that this is achieved is basically by hand authoring the normal directions of your planes for your tree. And so structurally here, you can see on our left, this is what my foliage was like originally. It's just a bunch of intersecting planes, and they are showing up at really odd defunct angles because they're flat to the light in all different orientations. However, that orientation in order to light doesn't have to be that way. So what I've done here as an example is I have matched those normals to a normal on a sphere. And what happens is you can see here the lighting on the right, as the lighting is hitting your bush or your shrub, you're seeing it light as though it was spherical, even though we've got a lot of different planes and we get a nice broken surface. And that's really how you do this sort of stuff. So the reason why I keep banging on about this sort of stuff is that, yeah, a lot of your information is coming from within your modeling package, and there's a lot you can do with that. If any of you are 3ds Max users, there's a tool called Nor's Normal Thief, which allows you to steal normals from another model, from one model to another. So yeah, that's how you can manipulate your normal in order to manipulate your lighting engine. In respect to normals as well, where we talked about tangent, this basically is telling you what orientation your texture normals. So obviously we add extra information with texture normals, and that just will tell when your lighting hits your surface, it adds a little bit of one orientation. That's what your red channel is. And then your green channel adds a little bit of other orientation into it. They're basically a vector map, and they're colored this way because you don't worry about your blue channel. Your blue is always basically 1 because your blue is almost always facing directly outwards out of your surface when you have a tangent normal map. One really important thing to remember is make sure you're importing your tangent maps, tangents, because if you're not importing your tangents properly, and there's sort of an example down here, you can end up with your lighting, especially around mirrored seams, being incorrect. And that is because what it has to do, what the tangent is doing, is telling the normals which direction are we facing. Are we pointing that way? Are we pointing that way? And you can end up with upside down orientation. So you can see here that it actually should be lit across the clavicle on the left. The lighting on the clavicle should be inverted, but it can be quite difficult to see. I actually might, and then basically your lighting either happens after everything's drawn to screen, or it will happen with each object as they're drawn to screen. I won't go into too much detail about this because it's not really important anymore. Mostly these days we do a combo of both, which is called forward plus plus, which is essentially where we create a series of maps from everything on screen, as well as doing individual lighting on these objects on screen. And then we use those pieces of information in order to do your post effects, like your color grading and your exposure. But at this point, we've sort of gone away from actually rendering your models to screen. And now essentially we're talking about how we're rendering the screen and whatnot. So yeah, I might stop now if we've got like another couple of minutes to answer a couple of questions.
We are just out of time, unfortunately.
Oh, no, sorry, I did run a bit long.
That's fine. I'm going to let you read the chat after this, but the chat went crazy. They had some really good questions, but Richard and Finn jumped in and answered a whole bunch of them for them in the chat. But yeah, no, that was a very dense but very good talk. A lot of people were saying they're going to rewatch it again.
Yeah, sorry, I had a lot to get through.
You did have a lot to get through, and there's so much in there, and there's some really good questions that people in the chat are going to wait to ask you once you get in there. But thank you so much.
I'll jump into the chat. All right, awesome. Thanks very much.